So today I'm going to present a work by John and me, which is children's cardinality knowledge isn't always beneficial. In the field of children's cognitive development, an interesting question is what is the relation between children's understanding of numbers in measuring discrete and continuous quantities? Do they understand that the 6 in 6 blocks and the 6 in 6 blocks long have the same meaning? Conceptually, the meaning of numbers in representing discrete and continuous quantities is highly similar. They both refer to the manyness of the units. So in representing discrete quantities, the 6 refers to the manyness of the units of the set. And in representing continuous quantities, the 6 refers to the manyness of the units of the length. So this might lead us to expect that understanding the sixness of a set of blocks, which is cardinality, would co-occur with understanding the sixness of a length of blocks, which is measure. So children's understanding of discrete quantities have been widely investigated. And a classic task that was used is a given number task. And in a typical version of this task, researchers repeatedly ask the child to give a specific number of items drawn from a larger set of objects. For example, researcher might ask the child to give 2 blocks from a basket containing 10 or more blocks. And of interest is the range of numbers to which the child gives. And if the child correctly gives the group question n of objects to n and no other, then the child is called a knower. And many studies using this task have found that starting from around 2.5 years old, children gradually extend the cardinality principle to a greater range of numbers. And there are also studies investigating children's understanding continuous quantities. And they found that initially, children do not use number words to measure continuous quantities like the length. And this was first found by Piaget and his colleagues in 1960. In their study, they provided children 2 conditions, and in one condition, 2 sets of blocks were arranged in 2 parallel rows, and with the 2 rows in perfect alignment. And children were asked to decide whether the 2 lines are the same length or not. And they found that when parallel, the equality was obvious, and 4-year-olds succeeded because they can solve this problem visually. And they also provided the other condition in which one of the 2 rows was modified by the introduction of angles. For example, one row is at right angles to the other. And they found that 4-year-olds failed because you have to count blocks to solve these angle problems. And this suggests young children are not using number words to measure continuous quantities. But they also found that 6-year-olds succeed in solving this angle problem, suggests that when they got older, children could use number words to measure continuous quantities. So back to our research question, what is the relation between children's understanding of numbers in measuring discrete and continuous quantities? And we have 2 hypotheses. And one hypothesis is that based on their similarities, children's understanding of numbers in measuring discrete and continuous quantities would co-occur. So they would understand the 6 in 6 blocks as the same as the 6 in 6 blocks long at the same time. Our second hypothesis is that one understanding would precede the other. It might be the continuous precedes the discrete, or discrete precedes the continuous. And to address this, we first created a given number task adjusted from Wien to test children's understanding of numbers in discrete quantities. Our given number task is a titrated computerized task where we show children a row of 20 adjacent identical blocks at the top of the screen and the blank areas at the bottom. And children were instructed to put 1 to 10 blocks in the blank areas by pressing the buttons. As in when after the child responded on each trial, we asked the child, is that n blocks, and can you make sure to ensure children were satisfied with their responses? And if the child was not satisfied, he or she could change the answers. And we also create a novel give a line task that was directly analogous to the given number task to assess children's understanding of numbers in continuous quantities. And similar to the given number task, children will show a row of 20 adjacent identical blocks at the top of the screen and the blank areas at the bottom. But they were told that this is one block long and these blocks stick together, and ask them to draw a line with 1 to 10 blocks long by pressing the button. And our participants are 90 American 3 years, 5 months to 6 years, 11 months old children. And our first research question is what children's performance are on the two tasks. And to answer this question, we plotted the PAE of those two tasks against their age. So the PAE here is a % absolute error, which reflects their accuracy. So the lower value is the better performance they are. So we found that, as expected, children's performance on the two tasks improved with age, but the performance on the given line task was worse than the given number task. And a more interesting question is, what are the relations between children's performance on the given number and the given line task? And we first divided children into different knower levels based on the given number task. And we found that in our given number task, half of participants were 10 knowers and the other half was scattered less than 10 knowers. And we thought these two groups might be something different. And sure it did. So we look at the performance of the given line task of these two groups on the given number task. So here the x-axis is the % absolute error of on the given line task, which reflects the accuracy of the given line task. And y-axis is density. So when we compared the distributions of 10 knowers versus non-10 knowers performance on the given line task, we found that on average, the non-10 knowers performance was less accurate than 10 knowers. So there's an overall positive relation on accuracy between the two tasks. But a more interesting pattern was found. We found that non-10 knowers PAE were distributed normally, but it's clearly that the 10 knowers performance on the given line task is bimodal, suggesting that the 10 knower comprise two distinct groups. So although the mean of the whole group of the non-10 knowers is less accurate than whole mean of 10 knowers, some 10 knowers are much more accurate than the non-10 knowers, and some 10 knowers are less accurate than the non-10 knowers. So it indicates that 10 knowers do not always have a better understanding of quantities than non-10 knowers. And if you look at the answers that they give, those two groups really pop out at you. So if you look at here, so we found that the slopes of 10 knowers regression line in the given line task showed two distinct patterns. And for one group, their estimates were perfectly linear, fit by a linear function with both the slope and R squared equaling to 1. In contrast, the remaining 10 knowers estimates were moderately well fit by a linear function, but their slopes were much smaller. By the way, in this plot, the subject numbers are linear related to their ages. So a higher subject number indicates an older case. So if you compare the age of these two groups, the below average 10 knowers were younger than the above average 10 knowers. So it's just that the below average 10 knowers error appears to be an immature sort of number knowledge. And when you look at the number of button presses to create a line, we found that the below average 10 knowers were more likely to link the number of button presses to the number requested than non-10 knowers. For example, they pressed the button 3 times when asked to draw 3 blocks long, and pressed the button 8 times when asked to draw a line 8 blocks long. And this is a reason that leads to the smaller slopes, but linear fit patterns of their estimates. So here, let me show you a demonstration about how they made responses. Here, I asked children to draw a line with 6 blocks long, and it should be like this. But part of 10 knowers just press the button 6 times like this. 1, 2, 3, 4, 5, 6. So in fact, 10 knowers made comically enormous errors on the given line task. They think that the line is 6 blocks long when it isn't even 1 block long. But no matter how profound their misunderstanding, given the patterns of children's answers, we found that almost all children showed an approximate understanding of numerical quantities in both discrete and continuous situations. So it means that they give more for larger numbers and less for smaller numbers. So in summary, we found that all children seem to understand that big numbers mean more of something. But children's understanding of numbers in discrete and continuous quantities are not equally accurate. And surprisingly, children's knowledge of cardinality is not always beneficial. Before they successfully understand how to construct a continuous magnitude using numbers, their understanding of cardinality interferes with their ability to approximately link numerical values to continuous extent. And our research has several implications. First, our results suggest a new developmental sequence in children's understanding of numbers. So initially, children start by approximately mapping numbers to spatial extent, regardless of whether it is a spatial extent of objects or the linear length. This state is not ideal because it yields less than perfect accuracy in both situations. And next, children begin to exactly map numbers to discrete quantities, such as objects and button presses. And this yields excellent performance on the given number task, but worse performance on the given line task. And finally, children accurately map numbers to both discrete and continuous quantities. So children's understanding numbers in discrete and continuous quantities turn out to be more complicated than co-occurring or one preceding the other. And second, our study also suggests that many of the children who understand cardinality also misunderstand numbers. Cardinality knowledge does not guarantee a very good sense of number. And a child who thinks that a line that does not even cover the breadth of 1 block is actually 6 blocks long seems to indicate a profound misunderstanding of what 1 and 6 mean. Depicting such a child as 10 knower may be a gross exaggeration of what they know about meaning of numbers 1 to 10. And also, previous studies have showed children's cardinality knowledge could predict their math achievements at school entry. And our studies suggest that many of these children also misunderstand numbers. And assessing their understanding of numbers in a measurement context may improve our ability to project their future achievements. So at last, I will thank my advisor, John Opfer, and all the lab mates at Ohio State University. I would also thank all the schools and participants in Columbus, Ohio. Thank you so much. I'm happy to take any questions.
Thank you for the very interesting talk. We actually have 5 minutes for questions. We are timed.
Hi, I just have a question in person. I apologize if I misunderstood this, but whenever you were presenting children with the framing of the build the line task, I thought you said that, like, how did you introduce the fact that one line or the little tiny line that you have on the bottom there? Because you had mentioned that there was this big difference between they'd click the button 6 times and it wouldn't actually go out. And I'm just wondering if maybe they were confused or making that mistake because of their experience with the give a number task, where they had to click the button 6 times and they sort of equated the two.
Mm-hmm. Yeah, so actually, yeah, it's a good question. Thank you. So actually, before we give the formal task, we have a practice session. And in the practice session, we showed participants what's the one block long is, and show them that they can use button presses to generate a long line. So yes, I mean, actually they have two strategies to draw the line, and one is like like press the button, once a time, and to press to generate a line, and or they can hold the button to generate a continuous line. And in the practice session, actually, we told the children that they can hold the button to generate a continuous line. So yeah, so that's why I don't think they confuse the instruction.
Thank you.
Yeah.
That's really helpful.
Thank you.
Is there any questions coming from the virtual site? Also, please feel free to type your questions on the chats. Any other questions? No? Okay, if there's no question, maybe we can hand it over to the next speaker.